Okay, now that we're done converting, we know now how to convert point in rectangular to cylindrical, rectangular to spherical, and vice versa. Now, how about if we want to convert is a vector from one coordinate system to another? And before we do that, we take note that when we are converting or transforming from one coordinate system to another, we don't we don't change the position of the vector or the point. It's still the same point. It's still the same vector. The only difference now is the name of the coordinate or the direction of the unit vectors itself. But the vector is the same. It's the same position. It's the same direction. So now, if we want to convert a vector from rectangular to another coordinate system, we need to review our concept of that product. If you remember the dot product, when you are taking the dot product of a, if this is a vector A, and you want to determine the dot product, it's just the projection of this into this direction. If you want this to be AR, then this projection, this is the dot product of A and that direction AR. So this is what we will do when we are converting from one form to another form or another system. We just solve for the projection of each of that vector into the direction of the unit vector that we want, because we are changing the unit vector but we don't change the vector itself. We are just changing the unit vector because we're changing the coordinate system. So if we are in cylindrical coordinate system, our unit vectors are arrow, AV, and AZ. It's not the same as before, AX, AY, and AZ in rectangular coordinate. So to convert that, we need to solve for the projection of the vector that we are converting into these unit vectors or into these directions. And to do that, we just solve the dot product. You take that vector itself, you take the dot product of that with the direction or the unit vector that we want. In this case, we want the raw a raw, a phi, and az, and so on. So before we do that, first we define the basic form, the component form of the vectors in rectangular coordinate system. This is how we write our vector ax, ay plus the z component. In cylindrical coordinate system, now instead of ax, ay, az, these are now this will change because we don't have the coordinates will be different, so the unit vector is also different. So we also have a different components. So here, instead of ax, a in the raw direction, we have a phi in the phi direction, and it's the same for the z component because the z in the rectangular coordinate is the same as the z in the cylindrical coordinate system. For the spherical coordinate, so this is the spherical. So instead of arrow, should be AR in the R direction. The R direction, AR, is outward direction, the direction of the radius. It's starting from the point, going outward. The raw direction is from the center of the cylinder, outward also, radial direction. Plus for the theta, A theta, in the theta direction, then we have AV direction. So these are the different forms in the different coordinates. Now, if you're given the rectangular coordinate system, this vector, you're given this vector. I want to solve, or I want to calculate or transform this vector into a cylindrical. So from rectangular to cylindrical. So you're given a rectangular vector, a vector that is in rectangular, it's written in rectangular form or coordinates. Now, to transform this, we need to solve for the components of the vector in terms of cylindrical components. So A raw, A phi, and AZ. And to do that, A raw, just like what I said, that is just the projection of the vector A in the raw direction. So to do that, this is just the vector, that product of the vector with the direction of A raw, because we're solving for the raw component. For the phi component, then you just take the dot product of the vector again with the phi. And for z component, it should be equal, but we can still try to solve this, but later on, the output is still the same AZ. The AZ here is the same as the AZ in the cylindrical coordinates, because the Z coordinate in rectangular is also the same as the Z in cylindrical coordinate system. And before we can do this, before we can take the dot product, because if you take this one, you dot it with arrow, so you will distribute that arrow. What is the dot product of AX and arrow? So before we can do that, we need to solve for the dot product of the unit vectors. Dot products of the unit vectors in rectangular and in cylindrical coordinate. So for example, A x dot a raw. What's the ax dot a raw? We don't have that in our previous discussion, but we can calculate that. And remember, just remember the definition of a dot product. It's just equal to the magnitude product of the magnitude of the two vectors multiplied by the cosine of the angle between them, the smaller angle between them. In this case, it's just a unit vector, so the magnitude is just 1. We just need to multiply it 1 multiplied by cosine of the angle between them. So what's the angle between AX and ARO? So if we go back into our drawing, just copy this one. This cylindrical coordinate here, so that we can visualize what I mean. So that is the direction of arrow. The arrow can also be written in, or starts at the origin. You can this is also arrow. So where is our AX? Our AX is in this direction. So what's the angle between them? The angle between them is just this angle. What is that angle? That's just equal to phi. So therefore, that product is just equal to cosine of phi. AX dot arrow is just equal to cosine of phi. Next, AX dot A phi. How about AX and A phi? Where is our A phi? This is our A phi here. So we can also write our A phi somewhere here. And what will be the angle between AX and A phi? Take note that A phi and A raw is perpendicular. They are perpendicular with each other. AZ, A phi, and A raw. Just like AX, AY, and AZ. They are always perpendicular. So if that this is perpendicular, this is 90 degrees. Then if you want to solve for the angle between AX and A phi, then that is just equal to 90 plus phi. So this is just the cosine of 90 plus phi. But what is this function here, cosine of 90 plus phi? We can rewrite this as cosine of 180 minus 90. Then we can factor out that 90. This will be minus phi. Then if you remember, cosine of 180, cosine of 180 of any angle, theta minus theta, they are always in opposite direction because they are 180 degrees apart. So if we draw this, if this is the theta, then cosine of 180 minus theta should be somewhere here because this is 180 degrees. So what does this mean? This means they are in the opposite direction. It means that it's just the negative. This one is just the negative of this one, or this one is just a negative of that one. So here, this is just equal to the negative of cosine of that angle, which is 90 minus phi, our theta here. And again, this is a cofunction. Oh, our identity in trigo, cofunction. If you take the cosine of the 90 minus angle, that's just equal to the sine. That's the definition of a cofunction. So therefore, we can just write this as sine phi. AX dot A phi is just equal to sine, negative sine of phi. So that's the dot product between AX and A phi. And lastly, we can also solve for AX dot AZ. This is just equal to, because they are 90 degrees apart, is equal to 0. Cosine of 90 is 0. Then for the y, for y, AY dot A raw. Let's go back to the drawing again. So just copy this one here. So AY is this direction, somewhere here. AY. Our arrow is also in this direction. Arrow. So what's the angle between them? This is the angle between them. This one. We know that this is 90 degrees. And this is phi. From here, arrow to the x-axis. So therefore, this angle is just equal to 90 minus phi. So if we take the cosine of that, that will be the dot product of AY and arrow. Cosine of 90 minus phi. And again, this is a cofunction. So AY dot arrow is just equal to sine of phi. Then next, AY dot AV. So what is AY dot AV? Where is our AV again? Our AV is somewhere here. AV. So what's the angle between them? This is the angle between them. What's that? This is 90 degrees. Arrow and AV. This is AV. Arrow and AV is 90 degrees apart. And AY is somewhere here. We know that this is 90 minus phi, and the total, if you add, because we're solving for this angle, somewhere here, this angle here, it will be equal to the 90 degrees. This angle will be equal to 90 minus this angle here, which is 90 minus phi. 90 minus phi. And this will be just equal to 90 minus 90 is 0. Negative of negative phi is just phi. So the angle between AY and AV is just phi. So the dot product is just cosine of phi. Cosine of that angle. AY dot AV. And next, AY dot AZ is again 0. Then lastly, for the Z component, AZ dot arrow, this is just equal to 0 again. AZ dot AV is also 0 because they are all perpendicular. These are perpendicular with each other. AZ is perpendicular to that. Then AZ dot AZ, this is equal to 1. So to summarize, we can just write the table to summarize our answers here. So this is the table, the dot product of a rectangular unit vector and a cylindrical unit vector. So now, if we want to solve for the components in cylindrical coordinates, so arrow, this is just the vector in rectangular, AX plus AY plus AZ. Then we dot this with arrow because we are solving for capital arrow. Then we just distribute that AX dot arrow. So AX multiplied by this one, AX dot arrow. What is AX dot arrow? So AX and arrow, it's just cosine phi. So if you go in the table, arrow and AX, so this is cosine phi. This is like a multiplication table in arithmetic. So you just multiply this with cosine of phi. Then plus AY, this one, AY and arrow. What is AY dot arrow? We have sine phi, positive sine phi. So AY times positive of sine phi. Then lastly for AZ dot arrow. AZ dot arrow is 0. So this term will be equal to 0. So this is now just our arrow, the component at the raw direction. This is the projection of that vector in the raw direction. For A phi, repeat that process again. You can just copy this. And just change this raw into phi. So what will be our A phi? So AX dot AV. AX dot AV. Negative sine phi. So negative AX times that product, which is sine phi. Then plus AY dot AV. AY dot AV. That's cosine phi. So this is AY times cosine phi. And again, AZ dot AV is equal to 0. So plus 0. So this will be our component at the phi direction. And for the Z direction, AZ, again, if you use the definition here, so this is AZ. We distribute that AZ, AX dot AZ is 0, AY dot AZ is 0, AZ dot AZ is 1 times AZ. So AZ is equal to AZ. Then collecting all the values now, the vector in cylindrical form can be written just like this one: ax cosine phi plus ay sine phi. This is our a raw in the raw direction, a raw. Then for the phi direction, the component is ay cosine phi minus ax sine phi. This is in the phi direction, and for a z direction, it's just az. It's the same, az. So this is the equivalent of that vector in cylindrical coordinate system. That's how we convert from rectangular to another form, cylindrical. You just take the dot product. For a spherical coordinates, or from rectangular to spherical coordinate. So here, first we need to again solve for the dot product of the unit vectors. So let's start with ax dot, this time it's ar. So where's our ar and where's our ax? So from here, this is our figure. Our ax is again somewhere here, while our ar is in this direction. So if we take the dot product, this is ar. This one is ar. With the ax, we need to know the angle between them. But before we take the dot product, first we need to project this ar here into the same plane as ax, which is at the xy plane. So we need to project it somewhere here. And this vector now, because it's just a projection of ar, this ar here, then to solve that, we just solve the dot product of that one, of the two vectors. And to solve for the dot product, because they are just unit vectors, we need to know the angle between them. So what is this angle here? That angle, this is 90 degrees. And this is theta. So it should be 90 minus theta. So that's the projection. So I just write it here. So that's just equal to cosine of the angle, which is 90 minus theta. Or just write it here. Cosine of 90 minus theta. But this is not yet the answer for the dot product, because this is just the vector here. And to solve for the dot product with ax, then we need again this one. And this is phi. So just multiply this with cosine of phi. So therefore, ax dot ar is just equal to cosine of 90 minus theta is the sine cofunction again. So sine theta cosine phi. So that's the dot product between ax and ar. For ay dot ar. So our ay again is somewhere here. So instead of going in this phi direction here, phi, this should be our angle instead of cosine of phi. So it's still the same. This is sine theta. That's the projection of ar in the xy coordinate or plane. So this is the sine of theta. Then that cosine will be this angle here. What is this angle? This is 90 minus phi. 90 minus phi. So you just multiply this with the cosine of that angle. 90 minus phi. But what is 90 minus phi? Cosine of 90 minus phi, that is just equal to sine. So this is sine theta, sine phi. And for az dot ar, it will be equal to, where is our az? Our az is this vector, unit vector. It goes upward, that is az. Whereas ar, this is ar. So what's the angle between them? It's just theta. So the answer here is just cosine of theta. Cosine of theta. And repeat this again for the other unit vectors. For the theta, so ax dot a theta. So if we copy this one again. So where is our a theta? This is our a theta here, somewhere here. So if we project it somewhere here, this is a theta. But again, we need to project this a theta in the xy plane or the xz plane in the ax plane. So we need to rotate this into this direction, and this one will be, again, can be solved. This angle between them is just phi. We just rotate this until here in the x direction, so that's also phi. And to solve that, this is equal to the cosine of the angle between them, and that is cosine phi. That's the projection again. Then after that, we take the dot product between ax and that vector, and this angle is just equal to theta. So just multiply it with cosine of theta. So therefore, ax dot a theta is just equal to that one, cosine phi times cosine theta. For ay dot a theta, instead of rotating into the x axis, this will be our ay here. So this is our new vector, the dot product again, the projection of a theta, and what will be the angle if you go into that direction. So that angle will be equal to, because this is 90 degrees, that will be 90 minus phi. So here, we will multiply this with cosine of 90 minus phi. That's the projection of a theta. Then we take the dot product again, and this angle again is theta. It's the same as that angle here, theta. We multiply it with cosine theta. And what is cosine minus phi? And that is just equal to sine of phi. Sine phi cosine theta. Sine phi cosine theta. Next, for az dot a theta. Az dot a theta. So our az again is going upward here. And our a theta is somewhere here. So what's this angle here? It should be equal to the angle between AR and a theta is. So if this is our AR, this is our AZ, our a theta is somewhere here. This is 90 degrees. And this is theta. So if this is AZ and this is a theta, what's the angle here? It should be theta plus that 90 degrees. So this is just equal to cosine of theta plus 90 degrees. But what is cosine of 90 plus theta? We already solved it here. Somewhere here. Cosine of 90 plus theta is just equal to negative sine phi. So AZ dot a theta will be equal to negative sine of phi. Then lastly, for a phi, for the a phi, ax dot a phi, so our a phi is this direction, in this direction, in this direction, somewhere here. It's the same a phi as before in the cylindrical coordinates. This is ax, this is a phi. So what's this angle? This angle will be equal to 90 plus phi, because this is 90 degrees here, and plus phi. So 90 plus phi. So this will be cosine of 90 plus phi. But again, cosine of 90 plus phi is just equal to negative of sine phi. Next, ay dot a phi. So for ay, instead of going here, you go in this this direction. This is our a phi or ay. So what's the angle between them? What is this angle? That is just equal to phi. Why? Because this is 90. 90 minus 90 minus phi. And that's just equal to phi. So this is cosine of phi. Then lastly, ay dot az. Ay dot az or a phi. Az dot a phi. Where is az? Our az is going upward. Somewhere here. While our a phi is in that direction. So this one and this one. What's the angle between them? They are perpendicular to each other because a phi is in the xy plane while our AZ is going upward. So this should be equal to 0 because they are perpendicular. Just like AC and AX. They are in the same plane. AV and AX is in XY plane. So this is now, these are the dot products of rectangular unit vectors and spherical unit vectors. Then to summarize again, we put it in a table. This will be the dot product between rectangular and spherical coordinate system. So if we solve for the components in spherical coordinates, so we have AR. AR is just equal to A dot in the R direction. So this is AX plus AY, AX plus AY plus AZ dot AR dot AR. Then we distribute AX dot AR, AY dot AR, and AZ dot AR. So this will be AR equals AX dot AR is sine theta cosine phi. So somewhere here, so AX dot AR sine theta cosine phi. And you multiply it with AX. So this is AX times sine theta times cosine of phi. Plus for AY dot AR, it's sine theta sine phi. So AY sine theta sine phi. And for AZ dot AR, it's cosine theta. So plus cosine or AZ cosine theta. AZ cosine theta. So this will be the value for the component in the R direction. For the theta direction, A theta, we repeat this again. But this time, instead of AR, it's A theta. First, AX dot A theta. AX dot A theta is cosine theta cosine phi. So this is equal to AX times cosine of theta cosine of phi plus AY dot A theta. That is cosine theta sine phi. Cosine theta sine phi. Then for AZ dot A theta, that's negative sine phi. So minus AZ sine phi. And lastly, for the phi component, we have for AX dot A phi, it's negative sine phi. So this is minus AX sine phi. Then plus cosine phi, that's AY dot A phi times AY. AY cosine phi. And lastly, for the Z component, that is 0. A phi dot AZ is 0. So there's no other term here. So collecting all this one, the vector now in terms of spherical coordinates will be, for R direction, we have so this is in R direction. Then for the theta direction, you can just copy this one. So plus this one is in the direction of theta. Then for the phi direction, this is the phi direction. So this is multiplied by A phi. A phi. So this is now our vector in the spherical coordinate. So those are the components of that. So this is how we convert vectors from a certain coordinate to another coordinate system.